Hello everybody, welcome back to the Gregorius Maths video. Today I have sort of an important announcement to everybody, and that is that I've discovered the true meaning behind 6, 7, which, I've been hearing an awful lot. And at first, my original conjecture was that people were making fun of Grothendieck, or however you pronounce his name, for saying that 57 was a prime. Perhaps they were pointing out that really he meant 67. But no, today I come to you with the actual answer to this question. And it all stems from the following equation. So the true origin of the meme stems from this. We consider k factorial times by k plus 1 factorial equals n factorial, where k and n are positive integers. Or they could be 0 as well, so non-negative integers, let's say. And you might be wondering how this relates to the 6, 7 meme. Well, okay, let's first of all get rid of the trivial solutions to this. So the trivial solutions to this arise when either k factorial or k plus 1 factorial is 1. So we could have the pairs being 0. If k is 0, then n is 1, or n could be 0, or we could have k equals 1, in which case n equals 2. So these are the trivial solutions. If you plug them in, you'll see pretty quickly why they work. And before I move further on in the video, I'm now going to show you footage of ChatGPT foolishly claiming that these are the only solutions. Okay, check this out, okay? I'm going to ask ChatGPT what the solutions to the equation is. Let's see what he says. The hell? This guy's really thinking. Aha, there you go. Final answer, all integer solutions are 0, 0, 0, 1, 1, 2. Right there. ChatGPT does not know about 6, 7. He doesn't know. Doesn't have. Let me let him know. All right, let's give him a. What about 6, 7? Now he knows. Now he knows. Back to the video. Okay, I hope you enjoyed that footage. Now, my goal is to show that the unique, non-trivial solution to this is 6 factorial, 7 factorial equals 10 factorial. So, how are we going to even begin to attack this? Well, okay, think about this, okay? So, firstly notice n factorial equals k plus 1 factorial times by k factorial. But k plus 1 factorial is just k plus 1 times k factorial. So this is just k plus 1 times by k factorial squared, okay? Furthermore, notice that the prime divisors of this guy are all going to be less than or equal to k plus 1. And so therefore, there are no primes in the interval between k plus 1 and n, right? Because if there was a prime between k plus 1 and n, well then we'd have an issue because a prime in this range would contribute, it would contribute a member of the prime factorization of n factorial that we would not be able to get from this expression here. So there's no primes between k plus 1 and n, okay, when this equation is true. Now, let's let q be the biggest prime, which is less than or equal to k, okay? Now, Bertrand's postulate tells us that that there is a prime between k over 2 and k, and since q is the biggest prime less than or equal to k, we can then deduce that k is that, well, what we can deduce is that q must be bigger than k over 2. So in other words, 2q must be bigger than k. And so therefore we can deduce that, well, q is less than or equal to k, but that must be less than 2q. So k lies somewhere between q and 2q. Okay? Well, what does this tell us? This tells us that in k factorial, we're only getting one power of q, because we don't get q times 2q. Like, because q is prime, we're not getting any extra factors of q. And so what we do is we take what's called the q-adic valuation, which is a fancy word for saying the exponent in the prime factorization. The q-adic valuation of n factorial is equal to 2, because we have k factorial squared getting in there. So there's a power of 2 in this prime expansion. Now, what does this tell us? Well, this tells us that n must be bigger than or equal to 2q. Why does this tell us that? Well, if you think about the definition of n factorial is 1 times 2 times blah 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 times q times blah 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 times 2q times blah blah blah. That's the only way it can get 2 powers of q in there, since, again, as I say, q is prime. So n must be at least 2q, otherwise the q-adic valuation would be less than 2. Hopefully that makes sense. Anyway, so we know that n is bigger than or equal to 2q. But now, consider the case when k is bigger than or equal to 7. If k is bigger than or equal to 7, then think about the definition of q. Q is the biggest prime that's less than or equal to k, but 7 being itself a prime, it means that if k is bigger than or equal to 7, then q must also be bigger than or equal to 7, since the biggest prime that's less than or equal to some number that's bigger than 7 will at least be 7, basically. Now, here's where we have an issue. There are such things as Ramanujan primes, and Ramanujan primes are primes so that there's a, okay, hold on. Okay, here, let me just state this. 11 is a Ramanujan prime, and it's R2, so R2 is equal to 11. What does this mean? This means that there are at least 2 primes in the interval x over 2x when x is bigger than or equal to 11. And so another reformulation, if you stare at this for a second, what you notice is that since q is bigger than or equal to 7, this must mean, well, okay, this means that basically for any interval bigger than like from 6 to 12, so for example 7 to 14, 8 to 16, so on, there must be at least 2 primes. And so since q is bigger than or equal to 7, this means that there are 2 primes in the interval between q and 2q. And notice here that this is an open interval, so q is not included in that. Now, what do we know about q? Well, whoopsie daisy. We know that q is the biggest prime that's less than or equal to k. And so any prime in this interval must be at least k plus 1. So, okay, at the very best case is that k plus 1 is prime. But we still have one more prime left in our interval. So there is at least one prime, p, such that k plus 1 is less than p, but is less than 2q. But this means that k plus 1 is less than p is less than n, because we showed that n is bigger than or equal to 2q. But this is a contradiction, because for this equation to be true, there must be no primes between k plus 1 and n, but we just showed that there is a prime between k plus 1 and n. And so we have a contradiction. And so what we can conclude is that k cannot be bigger than or equal to 7. And okay, we've ruled out the trivial cases. So all that's left to consider now is what happens when k is between 2 and 6. So let's look at that on the other side. So in order to aid our calculations here a little bit, let's just say that n is equal to k plus 1 plus some m, where m is bigger than 0. Then the equation k factorial k plus 1 factorial equals n factorial gives us that k factorial is equal to, and then just cancel out all of the terms in n factorial before k plus 2. So we get k plus 2 times by k plus 3 times by up until k plus 1 plus n, like so. Now, let's just start plugging in numbers, okay? We've only got 4 numbers to check. When k is equal to 2, we immediately have an issue because 2 factorial is immediately less than 4, so that's bad. Okay, we can't have k equals 2. Okay, let's try k equals 3. 3 factorial is 6. Now, 3 plus 2 is 5. 5 times by 6 is clearly bigger than 6, so we can't have k equals 3 either. Let's try k equals 4. 4 factorial, 24. But 6 times by 7, that's no joke, that's just, okay. 6 times by 7 is 42, so we also can't have k is equal to 4. And let's just check k equals 5. So we're sort of just doing it by exhaustion. There's only 4 cases to check here. K equals 5, we get 120. But if we plug in 5 here, we would get 7. That's too small. 8, so 7 times 8, 56. That's too small. But then if you do 56 times by 9, that's too big. So k equals 5 is not going to work. But here comes the magic. 6 factorial, that's 720. Plug in 6 here, that's too small. 6 times 9, that's 72. Sorry, 8 times 9, that's 72. 8 times 9 times 10, that's 720. So m equals 2. Sorry, m equals 3. And k equals 6 works. And so what do we get? We have 6 factorial, 7 factorial equals to 10 factorial, because k plus 1 plus m, that's n, so yeah, 10, that's where you get the 10 from, or you could just brute force calculate it. 6 factorial, 7 factorial is the only non-trivial solution. Hence, we have the origin of the meme right there. I solved it, guys. Don't worry. No need to thank me in the comments, although a thanks would be appreciated. Yeah, hopefully you enjoyed that. Hopefully, I mean, yeah, there you go. There you go. 6 factorial, 7 factorial. The only non-trivial solution to this equation. And hence, I've discovered the origin of the meme. So, you're welcome. And yeah, in any case, I'll see you in the next video. Hopefully you enjoyed, and